Okay. So the question is, based on this, please tell me, I'm going to write down here the question. What is the total? What is the total electronic energy of the system if it has 5 electrons? Okay. For a potential with a length A equal to 1 amp in length. So who can tell me what is the total energy of the system? It is okay. So we have have this case, please. Is that in this case is an infinite potential world. So please tell me what is the potential of this like this. And this is A. And the vector there is A. And you have now five electrons. Okay. So Bobby, I have 5 electrons. So what will be the electronic structure here?
And the second time, and level number 2. Now, yes.
I have 5 electrons.
Yeah.
So I put 5 electrons here. What will be the distribution?
2 electrons in the Pearson line.
4 electrons here. Why not 3?
For the exclusion power.
Power exclusion principle, right?
Yeah.
Okay, so 2 electrons here. How many electrons here?
3.
3. Bang, do you agree with this? What says the Pauli exclusion principle? You cannot put more than 1 electron with same state. State up, you cannot put like this. No, this not. It will cancel out. But you can put a spin down. So because the electrons has only a spin up, a spin down, we have this. So 2 electrons here, then 2 here, and 1 here. Please, I teach you this in 5th semester. That is not acceptable. Okay, please remember this. So, based on this, please, could you please tell me what is the total energy of the system? Right? What is total energy? Multiply by 5. Kinetic energy multiplied by 5 K. K what? Okay, please. I need now. I have 5 electrons. So what will be the total energy of the system? Yes, it's correct what Flora says. Here, since we have the potential cell, so the electrons only have kinetic energy. But how much kinetic energy has total energy? Bricks. Okay, so we know that E sub n is equal to, remember this, is pi squared h bar squared n squared divided by 2 na squared. Right? So what will be and remember we're going to use yes, that's it. So this is so what it will be the total energy brief? What will be?
So first just for the equal one,
How many?
2 times.
2 times. I'm going to put E sub 1 plus right? So 2 plus so 3. Okay, so here is that. So, and please, tell me what is that? What is the total kinetic energy? Is that clear, this, please? Remember, first of all, is probably the last time we're going to do at this very most fundamental level this kind of electronic structure. 2 electrons because of the Pauli exclusion principle, right? And this for fermions, for in the case of electrons, the fermion has only spin up and spin down. That's the reason you can put only 2 electrons in the same energy level, right? And that's it. Okay. So what is it? Will be the, so I'm going to put the E total. The E total. The E total is equal to this, right? 2 times this, the sum. I'm going to put like this. Sum, right? Of n square. I'm going to copy this formula, please. See? Comma. N from 1 to 2 plus this. You see, that is the way that I am going to do this, replacing n to 3. See, that's the one way to do it. And I have to replace A by in meters. 1 Armstrong is 10 to the minus 10, 1 to 10 to the 1 times 10 to the minus 10 meters. So I could do in joules this. H bar is it is H, that is 6.626 times 10 to the minus 34 divided by 2 pi. And m, but the mass of the electron is this, right? Mass of the electron 9.1 times 10 to the minus 11 minus 31, so kilograms. So this is in joules, right? This is in joules. This will be the total energy in joules. Right. If you want in electron volts, we have this. So it's just, we have to divide this value divided by 1.6 times 10 to the minus 19. This will be in electron. Okay. So, okay, just in case, how to put this, how to put this. This is script, space SC, capital E. Okay. H bar is escape. HB escape. Escape. HP escape. Okay. We want to put these symbols here. Okay. Don't forget to save this. Questions here, please. Question. Juan, can you see this? Luis, can you see this? Okay, it's okay. The size is fine. Okay. Let me know if I can continue, please. I'm going to pause this here. Let me pause. So now we are going for the single finite. potential? Well, model of a single atom. Okay, so this will be a section, please. Select here, and I put this as section. Format, sorry. Select this, and we put here section. See? So first of all, let's define the potential. Right? So the potential, please do not repeat anything again. So just copy and paste this, we did this. Where is the potential here? Look, I'm going to copy this, please, and paste it here. So V of X now is not like this, it's V0. Please do not use capital letters, okay? Please do not use capital letters, just put V0. When X is less than minus A over 2, see? Look this, how it is. Okay. We're going to solve this problem. Shipping. We have this problem. Okay. Okay. So now we should start to solve. So first we propose this. And now I'm going to do the following, right? So in this, we are going to today why we use this. We're going to use atomic units. So in atomic units, remember, H bar becomes 1, the mass of the electron is 1. In that case, the position, the units of the position is in Bohr, right? Bohr. And the energy, if that is the case, is in Hartrees. In Hartrees. Okay? That is the units of the energy is in Hartrees in this case. So I repeat again. If we use atomic units, so H bar becomes 1, the mass of the electron becomes 1, the positions will be measured in Bohr. So remember, 1 Bohr is 53 angstroms, and consequently the energy will be in Hartrees. Okay? So this is the question will read like this, showing a question will read like this. So very simple now. 1 over 2, second derivative of I with respect to dx squared plus b phi of x, and that is equal to 3 times. See? So that is the question now we have to solve. Okay. So let's define first of all the potential, please. In that case, we are going to put LA, length of A, 2. I'm going to use 2 Bohrs, okay? So please comment that this Bohr. Bohrs, right? And B pot, that is equal to 6.5. I'm going to use 6.5, please. That is in Hartrees. I'm going to put the notation is E sub H. That is Hartrees. Okay. So we're going to use this because as I'm telling you, it's not possible to have an analytical solution for this potential. So this is that we are going to check some numerical solution. We are going to keep this from now on to use this kind of solutions, okay? So I'm going just to remind you this okay, I'm going to, yes. In atomic units, H bar becomes 1, right? Comma, M, the mass electron also becomes 1, comma. Also, the charge of the electron, well, here we don't need it, but charge of the electron also is 1, here. Then the length are given in volts. right? One ball, just for you. Ball go to 0.53. Okay, and the energy in hertz that we are going to take E sub h, right? Comma, just in case to have the conversion one Hartree is equal to 27.21 electron volts. Okay. So this is just some note here to this, okay? Now we're ready to plot this. So let's plot it. Please, to plot this, do not repeat this or what we did before here. There is a plot here, and we don't, no, I don't have this. Let's repeat this here. So we're going to plot this, please. Let's put this plot, P of x. I'm going to replace, since this potential is equal now, I'm going to put P0. I'm going to put B pot, comma, and A I'm going to replace by LA, right? So you have this, comma, X I'm going to put from minus 2.3 to 2.3, comma, and now let's make this axis level. So X is X, comma, and B of X, comma, plot style, going to put red, comma, thick, red, comma, thick, comma, plot range, I'm going to put automatic in X, comma, and from minus 0.2 to 7.2. Comma, access style. I'm going to put arrow heads. Like this, right? 0.0, comma, 0.03. Okay, comma, billings with good access. Okay, and let me see it works. There it is. Okay, so this is so we start plotting this. This is the first step to know your potential is fine, is just plotting this potential. So that is what I intended. Don't forget to save it. Let's put this in plot. So the next thing is we're going to put a section solving the Schrodinger equation in atomic units. So remember, in atomic units, we have that, right? So this will be, please put a subsection, please. Solving this, right? So my equation one would be, I'm not going to write in the whiteboard because I can do this very quickly. This equation is minus 1/2, right? Multiplied by the second partial derivative of phi with respect to this. So I'm going to use this, sorry, I'm going to use here instead to write it and put phi 1. By 2 like this, right? So this will be my auxiliary wave functions will be P1, P2, and P3. So will be minus 1, this phi 1. So how to put this Phi, you can put escape, F escape. This should right hand this, no? This escape, F escape. So to have the same notation. Phi 1 and 2 primes, please, of X. I'm going to explain this, how to put this 2 prime in the English keyboard. Please, I repeat this again. How to put these 2 primes in the English keyboard will be this. So keyboard viewer, and look this. In the English keyboard, I need this one, right? This here is this one. In the Spanish keyboard, that is the the symbolic way to put the second derivative is this. So I'm going to put in the Spanish keyboard. Spanish keyboard is this, please. It's here. It's next to this 0. This one. That is the second. If you have a Spanish keyboard, you have to use this symbol here, this small line here, this like comma like. That is this, okay? So that will be in a Spanish keyboard. Anyways, it's recorded, so you can. I have an English keyboard, so it's okay. Of X, right? Plus B7, right? Times 5 X. Of X equal to the energy times 5 of X. That is my equation. That is the Schrödinger equation for the region 1 in atomic units. How to solve this? We do this. This solve this equation 1. In what function? The 1 of X, comma X. The solution is this. I'm going to pause here. Now let's do for the second part. So for region, this is region 1. This is region 1. This is region 2, and this is region 3. So I'm going to do for region 2, please. For region 2, equation, I'm going to put equation 2. Equation 2 is this. I'm going to copy this, please. Paste it here, and to edit this, will be dot. What is the potential? 0, right? Because it's 0 times 2. And this is 2. That is my equation 2. So we're going to solve this, please. So copy, paste here, and you change this equation 2 with phi 2. This is the solution. Solution is a function of cosine and sinus. So this basically it's telling you that within this region, we have a plane wave, right? Because the potential is 0. So that's the reason we have this. Okay. And finally, for equation 3 is equal to this. I'm going to copy this, please. Paste it here and change it, right, to 3. Here again, we have B0 by 3 by 3, right? That is my equation 3. And we're going to solve this, right? So I'm going to copy this and change the equation 3 with phi 3. That is back these solutions, okay? Don't forget to save it. I'm going to pause this here. We're going to do this simplification, okay? Let's define, let's define, right? Alpha, how to write this? Escape, escape is alpha, equal to the rho square is control 2, rho square, control 2, please. So 2 times b sub 0 minus this. And beta equal to the rho square. Sorry. Beta is control 2, rho square of 2 times e. Right? Remember this, right? With this, look this, what I have here, right? I have, look this. In this case, I have C1 e to the alpha x plus, I'm going to put C2 e to the minus alpha x. Look this. That will be phi 1. Phi 2 will be C3, right? Cosinus of beta x plus C4 sinus of beta x, right? And finally I have C5 e to the alpha x plus C6 e to the minus alpha x. Well, this is when x lanchas that is equal to this, you see? There's a over 2 minus a over 2 x a over 2, and finally x is when bigger a over 2. See, I have this. But for boundary condition, the boundary condition says the wave function in this case has to become 0 when x goes to either minus infinity or plus infinity. So you see, when you go to the limit of this, the limit, when x goes to minus infinity of this, c1 e to the alpha x plus c2 e to the minus alpha x, how much is this? When it goes to minus infinity, this 0, this goes to infinity, right? So it is not possible. Therefore, in this case, C2 has to be equal to 0. Why? Because we know that the limit when x goes to infinity or minus infinity has to go to 0. The only way is when C2 is 0. That's the reason. If C2 is 0, the limit of this goes to 0. So we are good, right? Otherwise, goes to. So therefore, C2 is 0. I'm going to raise C2. I'm going to leave it just like this. Do this. Now I'm going to raise this, so I'm going to put this C2 and C3 just to write down, notice, keep only the ones that survive. And you see here, again, the limit when x goes to infinity of C5 e to the alpha x plus C6 e to the minus alpha x. How much is this? You see, when it goes to infinity, this goes to infinity and this goes to 0, right? So it's infinity again. Therefore, you see, what happened here? C5, you see, so C5 has to go to 0, right? Therefore, C5 goes to 0, so I'm going to have like this, C4. This is my, at the end, that is the functions that I need. Okay? And that's it. I cannot simplify more. In this case, using these extremes of the wave function, because remember, the wave function has to decay to 0 in this kind of potency, right? So we know this is not a compare. Therefore, we're going to define this, right? So let's define this. First of all, we're going to do, please follow me, please do subscript. So because we're going to use subscript here of sigma I. You see, I'm not using capital letters, please be careful. Is equal to this. So in doing this, because I'm going to reset every time you work, you reset in this way, this e comma 4. Why e comma 4? C sub I goes from 1 to 4. That's the reason why. Okay. So the same for this. Now we have 3 wave functions. One, so we will do subscript. And instead of C will be escape, not phi sub A, equal to point, comma, I comma 3. Why? Because we have 3 auxiliary waveforms. Okay? And finally, I'm going to define phi sub, you see, control 1 of x. I'm going to define just the wave function right now. Point is equal to C sub 1 times the exponent of, you see, alpha x. See? Double color. Phi sub 2. How to put sub is with control. Remember, control minus 2 of x, 2 points equal to C sub 2, control minus 2 cosinus of beta times x. Remember to put the space in between alpha and x. No. So x has to become green, by the way. C sub 3 times sinus
of x. Right? And finally, the wave function I sub 3 control minus 3 of x is 2 points equal to this. This is 4 times the exponent of minus alpha times x. So these are my three wave functions, okay? Shivenda. Don't worry about this because we do this in this way so we can every time repeat again this and there is no conflict because we are assigning values, you know, that's the reason. We're assigning values to C1, to C3 later on, so that's the reason why. I'm going to pause this here. Okay, now we are going to define the wave function phi, right? So it would be like this, you know. So you enter this, but before we start doing this, just copy them. So copy this, please, here, and just you do not waste time, and you just change this, right? So it would be phi, see, of x, 2 points equal. This would be phi 1 sub 1 of x, see? See? And I copy this and paste everything here and I change the subindex. Phi 1, phi 2, and phi 3. See? There it is. Piece of cake. Just copy paste and after just you rename this. Remember, this now is phi, is a wave function, right? So I'm going to pause. Now we have to define the boundary conditions, please. We have two boundary conditions. In these two boundary conditions, remember here in this region, so it means that phi 1 of minus a over 2 has to be equal to phi 2 of minus a, right? So this is continuous and smooth. It says that phi 1 prime, that is equal to phi 2 prime of minus a. Remember this? So this means that the wave function has to be continuous and smooth. Continuous means that the wave functions in this boundary has to be exactly the same as the other region. And smooth, that means that the derivative of same in the other one. Here, phi 2 on a over 2 has to be equal to phi 3 on a over 2 and the derivatives. You see? So we are going to use, in total there are 4 conditions. So each boundary condition brings up 2 equations, right? So let's put these equations. So I'm going to put equation 1. Okay. First boundary condition is this, please. You can use that, please. Phi 1 of x, okay, minus phi 2 of x, replacing this x minus a over 2, see? That this has to be equal to 7. Question 1. Okay. Equation 2, I'm going to put here. And equation 2 is the same, but just derivatives. Not this very easy. So you enter the same, C, Control V. You change this equation 2. And you put the primes. After the 1, please, you see, after the 1 here, you have to put prime. Of the derivative, that the ones we use to enter the Schrodinger equation, right? Prime. And that's it. Equation 3 equal to this, right? I'm going to, if you like, you can copy and paste, but you have to remember to change this, right? So will be, in this case, will be phi 2, right? Phi 2 here. And phi 3 here, please. But not in x minus a over 2, now it's in a over 2. That is the other boundary. A over 2. And finally, you can copy this. This is here, and you put the primes. 2 prime, phi 3 prime. A over 2. That's it. We have 4 equations on the boundaries. And remember, this is equation 3. This is equation 4. You have to have equation 1, 2, 3, 4, and you have phi 1, phi 2, phi 1 prime, phi 2 prime, phi 2, phi 3, phi 2 prime, phi 2, phi 3 prime. You see? And remember the boundaries, right? This 2 is when x is goes to minus a over 2, and the last one is when x goes to a over 2. Shivendra, that is the equations. I'm going to pause now here, so everybody gets this. So I repeat again here, please. So as you can see, this set of equations here have coefficient C1, C2, C3, and C4. So we can make, to extract the associated matrix from here, in such a way will be M multiplied by the vector C1, C2, C3 equal to 0. To get this matrix, we can use this coefficient arrays of this, right? So the coefficient arrays of this table equation I. So it's because remember we have 4 equations. That's the reason I goes from 1 to 4. And what elements we extract is the C1, C2, and C3. So if you do this, you're going to have this. See? Please check this. Everything is correct. Matrix form. So it's easy for your eyes to see this. Okay? So you have to get exactly the same matrix. Okay, I'm going to leave it like this, and I'm going to pause here. Allow me, that's okay. So I'm going to repeat this because it was not recorded. So this, we have to find the determinant of this. Since there is no analytical, if you do the determinant of this equal to 0, we are going to have a polynomial, right? And we have to solve it. There is no analytical solution. That's the reason we have to get the numerical solution of this determinant, of this matrix, sorry. And the first thing is I have to replace for this matrix here, what is alpha and beta. You see, alpha is this, and beta is this. Okay, and this. If you do this, please, you're going to get this. Okay. Somebody's asking how to put the Rho square of 2. So let me put this. How to put this Rho square? The Rho square is control 2. 2 times. So is control. Put control 2 is this. And after you can put this inside. And so on. And now we are going to plot this. So I'm going to plot. So now, as you can see, this matrix is the independent variable is the energy E. So I can put this the determinant of this matrix, right? Matrix 2. In what range? In the range that I need, right? I need the energy changes from 0 to the potential, right? The potential is B-pot. That is that is what we call the bounded states. There it is. So it means that we are looking for solutions with determinant 0. So it will be when the energy is this value, and this value, right? So one very nice feature of this Mathematica that you can get approximate numerical solution just from the figure. So I'm going to put figure equal to exactly the same, please copy this, paste it here. But I'm going to make a zoom around this region. I'm going to take a zoom of this region. I'm going to take a zoom of this region, very, very small. So I want to see exactly where are the roots. So according to these plots, I'm going to put like this, comma, and I'm going to put plot range from minus 10 to minus 20, you see. I'm going to do a very high, then to minus 1. Okay. If you do this, I'm going to zoom this and you see what I'm going to get this. So it means that the energy levels I'm looking for is this value, and this value, right? So now I have to extract this information, as you can see here, right? So I'm going to extract this information. So, okay, I'm going to pause just 1 second here. Okay, so as you can see from Mathematica, this figure has a lot of information already here, right? Because if you have the plot, you have to have the information of this. So let's explore how Mathematica has the expression figure. If you put like this, there it is. So basically, the first approximation of the roots or in this case, the energy levels is this one. 0.74, the first energy level, 2.90 something, the second energy level, and 5.92, the third energy level. You see? So there are three energy levels, and this is approximate values. So I need to extract that information. You see? So first of all, I want to check this, how to extract. I need to get this. See, I need to get this information here. Where it is? This here. I need to extract this information. So to get this, for instance, I can do this. Just sometimes it's for trial and error. I think it's going to work like this. Let me check this. 1, 2, 3, 4. Let me see. Yes. Let me see what to do this. Very good. I need this. I need the 1, 2, the 3. This is 3. I suppose this is 3 here. No. So I have to do this. I believe it's this common. There it is. You see? So this is the way how sometimes it's by trial and error, because depending on your version Mathematica, it might change this. You have to take out 1. I don't know. It depends. So in my case, the word for Mathematica, I have a 14.3. So 14.3 will work like this. If you have the 14.2, 14.1, you have to raise one of these, and that's fine. So for that reason, I got to this, the approx root, right, is equal to this. Big one, this one. But I have to extract this, So I'm going to put this comma 1. You see? If you like this, you will put this comma 1. Like this, Well, it doesn't matter anyways. From 2 to -1. See? If you do this, if you check this, I'm going just to extract this part here. So this is in a way redundant, but I'm going to put like this. You see? So, but I need to extract these values. How to do this? Just to do this. Okay. This, and now I'm going to map. See? The hashtag 1, 1, 1, right? This and so this is to extract the values, these values here. I need these values here. See? Comma, hashtag, right? This. Map and this sort. So that is the way that I extract these values. There it is. So these are my initial values together. This is not the exact values, I mean the most accurate values, but this is from the figure, you get some these values. So this is, as I mentioned, this is, I mentioned before, this is the energy levels, the approximated values of the energy levels in cartridge, please. So to get this, the actual values, I'm going to put vals, so the values of the roots, the more accurate values, so to use this. After I'm going to put the famous fine root. Map, fine root. See, fine root. Or what? Of this determinant, mat2. See? Comma. Open this. This in what variable is e, comma, hashtag. See? And after this, I put this and, right? Comma, hashtag, right? And after this and after I'm going to move map, and I'm going to put these values. So you have to give here e, you have to give the approximate values of the roots, otherwise it doesn't work. So I'm going to put like this, and, comma, hashtag, right? And this is it, right? So as you can see here, what I'm going to do with this is I'm going to use these values here in this for each value of the, and after that you are going to do these values. There it is. So this is the most accurate values. These are approximate values. These are the most exact values using this file, and that's it. But it's very fast. You can do it analytic, you can use the other way, just find the solving the equation and get this is going to take ages. So this is the fast way to do this. Okay, and that's it. Please save it and everything, and we are, for now you have the values of the energy levels, and from these values of energy levels, we are able to compute even the constants, C1, C2, and C3, and C4, depending on the region that we are, okay? So there it is. Please, everyone, till here, I'm going to pause this. Okay, so now we are going to explore the level 1. Level 1, please. This will be a subsection, please. Subsection, okay? So I'm going to start. Nval will be for the first level, comma. And I'm going to do this. Do subscript the script of C, comma R. The same as we did before, right? But I'm going to put like this. So point, comma, a comma, right? First of all, I set up the constants. I erase any record of the constants if you did it before. And now I'm going to do this. Evaluate. The solution of this matrix here was what we call this the null space, So we're going to do this table, right? C sub I, comma 4, right? And this is equal to mat2, please. Replacing this value at rval, the ones that we computed, nval. In this case, nval is 1, so I put just. And after this, we have to do this. Now to null space, right? And after this, I'm going to put. And after, I'm going to put chop to make it. Okay. So what I'm doing in this is I'm going to find the set of values C1, C2, and C3 in such a way that belongs to the matrix which determines 0 for this value. The first value is one. I'm going to do this. Okay, let me check this. Everything looks fine. That's it. There it is. So this is the C1, C2, and C3. One of the solutions, right? Because there are infinite values. This is the ones. Okay. For C1, C2, and C3, and C4. Using this. So it means that these are the C values that if you multiply by this determinant, we're going to get 0. Okay. So we have this. Now we need to normalize, We need to normalize the wave function to find the wave function. The wave function to get the constant, the normalizing constant. Okay. For this wave function, right? I of x, right? Just in case the infinite is state in state. Okay, infinite is this. So we're going to put this normalization constant. I'm going to put int is equal to the, and we'll have to integrate. Right? So we have to integrate the wave function, So how to integrate? We need this, right? So we need to integrate this wave function. Minus. So this, what has to be this, please? Has to be equal to 1. So
since we have this wave function, so it's a constant here, multiplied by this, has to be one.
So we want to find the normalization constant. So let's do this, right? So for basically we want to do this. Escape J escape conjugate of x. Escape con, right? Times this. Okay. How to put conjugate is this. So escape conjugate is this, we already know. Escape conj escape. This is the conjugate of phi is this. So this is this replacing, right? Replacing alpha. This, you're going to use this. Do not repeat. Do this, please. Replace this, copy this part here. Where is this? Copy this part here, please. Alpha this. Alpha this. And now we're going to replace this. Replacing now. This, the energy, right? It is R val 1, R val, sorry, R val, N val. Right? With double, this is with double brackets. Right? Comma. And we have B0 is a B pot. Everything with small letters, no capital letters. And A is LA. Right? After this, you do evaluate, comma, and the integral goes from x goes from minus infinity to infinity. Right? So this is the, from here we're going to have the normalization for the whole wave function, right? Shivat. There it is. So this value is important because I have to use this value to normalize this wave function, right? Because if you do this integral, right, there is a constant here. So I'm going to put this c squared, right? So this has to be 1. So c squared multiplied by this minus the infinity of sine conjugate by dx. That has to be 1. Therefore, c is equal to this 1 over rho square of this, right? You see? That is a normalization constant, what we are looking for. Right now we get this, you know, we're going to get this. So this is, you know, this is the one of the rho square of this. Well, we're going to check it out. So please try to get this value. I'm going to wait here till everyone has the same.